Yeah, so let me motivate why we actually care about black holes. So probably not needed for this audience, but still to put some perspective. We have, of course, the holy grail, the quest of a theory of quantum gravity, and a black hole together with the early universe, probably the best laboratory to study that. I'll not talk about that. We have a cosmological motivation to look at the centers of galaxies. How did they grow and merge and get there? That will tell us something about the nature of supermassive black holes, but also about the history of our universe, and particularly if we're going to be able to match the scales all the way from the horizon to the galaxy scale, we can really learn something about that. Why now? Why do we care about black holes right now? Well, there has been a wealth of information coming from observations. We have the Event Horizon Telescope image. We have, this is Amity 7. We also have an image of Sagittarius A star in the center of our own galaxy. We have gravity interferometry measurements of blobs moving around the black hole in the center of our galaxy, winning the Nobel Prize. We have JWST. I keep forgetting the laser doesn't work. We have the JWST data here of flares from the galactic center. This was something I was involved in myself, actually, and we have extremely good time and space resolution of infrared flares. We have the real-time formation of a jet there from an AGN, where you see the bright blobs emerging from the center together with the formation of a corona. And we have a neutrino observation now, not diffuse, but actually localized to an AGN tentatively, I guess. So lots of information. And then on top, we have a lot of information coming up, hopefully, from merging supermassive black holes, merging galaxies, that can bring us electromagnetic counterparts to gravitational waves that can be observed with LISA or pulsar timing arrays. We have interesting optical flares, for example, from OJ287 that have been observed since 1887, I think. So for a very long time, that can potentially be an EMRI, an extreme mass ratio end spiral, as you can see here in this picture on the right. We have quasi-periodic X-ray signals that we may associate with orbiting things through an accretion disk. So also in merging objects, there is a lot of information out there and a lot more coming that can teach us something about the nature of galaxies and black holes. And to model all of this, we need plasma physics. And typically the plasmas around black holes are relativistic, and I'll tell you what that means. The relativity of a plasma is indicated by the sigma parameter, which is the magnetic energy density over the rest mass energy density. So sigma, a large sigma, means magnetized plasma, meaning there is a lot of potential energy. On the Earth, for example, in the Earth's magnetosphere, the sigma is typically smaller than 1. In fusion reactors as well, in the sun as well. Neutron star magnetospheres, the sigma is very, very high. And around black holes in an accretion disk, the sigma is typically of the order 1 or a bit lower, but in the magnetosphere or in a corona or in a jet, the sigma can again be very, 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 very high. What does that mean? Typically, this can make a plasma collisionless, meaning that the mean free path of an electron to hit something else is larger than the size of the system. So electrons don't collide. It means that the alphane speed, so the typical speed of waves in the plasma, can be of the order of the speed of light. And it means that Lorentz factors can be much larger than 1. And that's both Lorentz factors of the bulk motion and Lorentz factors of individual particles. And then there is a huge scale separation because of the magnetization. The Larmor radius, so the gyration of an electron around the magnetic field line, is much smaller than the system size. So we have a mean free path being much larger and the Larmor radius being much smaller. Now that is promising because that gives us a large reservoir of magnetic energy. Because of the collisionless nature, particles can really accelerate and can power high energy radiation that we can observe and do observe. But there is a question there because a magnetized plasma is happy to remain magnetized and doesn't necessarily radiate. So we need to understand how to extract that magnetic energy from the plasma and transform it into the radiation that we're observing or hope to observe. Well, that's a difficult question to solve because you need a whole bunch of physics. It's also what makes it interesting. Because the plasma is magnetized, you need special relativity. Because there's strong gravity, you need general relativity. Because the plasma is collisionless, you need kinetic theory. You need to solve a Boltzmann equation. Because we deal with high energy emission, we need to understand the radiation, but also some quantum electrodynamics, scattering, pair production. And due to the nonlinearity and the large scale separations, you typically need numerical solutions at very high resolution to resolve all the physics and all the scales, which is pretty much impossible. So the difficulty in this field is not that we don't know which equations to solve. It's not that we're trying to find the theory of everything we need to solve. No, we know the equation. This is the set of equations. It's a Boltzmann equation. This specific one has no collisions. You see a 0 on the right. And in the green and the red, you see the electric and the magnetic field. So the force here is the Lorentz force. So this is what we call the Vlasov equation. It's a special form of the Boltzmann equation. And these are the Maxwell's equations for the electric and the magnetic field. This is the source term summed up over all the charges. And here is a current, which is also summed up over all the charges. So this is a set of equations. It's a multidimensional, nonlinear many-body system. And typically we solve this with a particle in cell code. And I'll say a bit more about that later. So we know how to solve this set of equations. It's very expensive. You can add radiation into this system. You can do this in curved space-time. You can add all the physics that you would want. So why is this difficult? Let's go back to our M87 black hole. M87 has a jet, which we have observed in multi-wavelength. The jet is about more than 1,000 light years long, and the size of the event horizon, the dark region here in the middle, is 0.006 light years in radius. So there's already 6 orders of magnitude there. And then if you calculate what the Larmor radius of an electron is in the typical electric field, which is roughly, say, 100 Gauss around this black hole, then that Larmor radius 10 to the minus 11 times the radius of the horizon, roughly speaking. So there's 17 orders of magnitude there that you need to bridge to capture all the physics. So far, there have not been any 3D global kinetic simulations of such a system, simply because it's too hard. But there is an intermediate solution, and that is magnetohydrodynamics. And magnetohydrodynamics works reasonably well because it can capture the large scales and a little bit of the small scales. And those scales, they interact nonlinearly through instabilities, turbulence, dynamo effects, and so on. With magnetohydrodynamics, we have shown, not me, but the GRMG community has shown that we can study accretion and the launching of those jets, at least to some accuracy. So what is magnetohydrodynamics? You take a fluid approximation of your Boltzmann equation. You take moments of your Boltzmann equation. That gives you a reduced set of variables for the mass density, the velocity, the energy, and still the electric and the magnetic field. This is a set of equations in short form now. So on the left, you have the mass conservation and the energy momentum conservation. So this is nothing else than Navier-Stokes equations, conservation laws. And on the right, you have the same Maxwell's equations, just written in covariant form for space. So what people typically do is they assume an ideal MHD approximation. For that, you need to assume that the plasma is collisional, so the other limit than what we're actually in, and that the plasma is thermally equilibrated, so a single temperature Maxwellian for electrons and ions. Both those assumptions are wrong in the jet and in the accretion disk. Also, people assume typically that the plasma is a perfect conductor, meaning that in your co-moving frame, if you move with the fluid, your electric field is 0. E is equal to minus V cross B, so this adds up to 0, meaning there is no electric field that can accelerate your particles. So what I did during my PhD is that I added a small component to this framework, by developing a resistive relativistic MHD code. By now, it's accelerated on GPUs. There is adaptive mesh refinement. So we're actually able to resolve small resistivities, and I'll convince you of that later, I hope. This is difficult because your set of equations is not hyperbolic parabolic anymore, but it has a stiff source term suddenly that you need to solve. And we solve this with an implicit method. This is the source term here, and you see here is your resistivity. The resistivity is a proxy to capture dissipation, for example, magnetic reconnection, turbulence, and it requires high spatial and temporal resolution. The nice thing about this implicit explicit method is that on this right-hand side, you can add more non-ideal physics that you may be interested in: heat conduction, viscosity, and so on. This was all done in an open source code called BAC, the black hole accretion code. Right. Now, great, we have an electric field, but we still don't have particle acceleration, which leads to the radiation that we're observing. So we're still missing a piece. And for that, we developed a test particle module in our code, so we can evolve particles that do feel the electric and the magnetic field from the magnetohydrodynamics, but there's no feedback. So we're not solving this full cycle that I showed on one of the first slides. We're only solving the motion of the particles and no feedback. But we can be clever about that. We can use that on the size of the gyro radius of a particle. The force of gravity is pretty much negligible. Gravity acts on large scales. Electromagnetic forces act on relatively small scales. So you can separate them, or numerically speaking, you can strength split them. So what we did is we used a method used in special relativity, the Boris pusher, ported it to general relativity by separating a geodesic term, so the motion due to the gravity, and an electromagnetic term. This was pioneered by Kyle Parfrey and by Fabio Bacchini, with whom I collaborated. And recently, Minggao Zhao, is actually a high school student that I worked with, realized that this splitting can also be used to add more forces in this part where you do the Lorentz force, so in the locally flat part where you don't care about gravity. And he implemented, for example, radiative losses, so a scattering of protons and photons, which is interesting for neutrino interactions. So in this way, your particles do feel the resistive electric field. They can accelerate, and they can interact with photons, with other particles, to get the radiation out that we want to explain. Now, this is difficult because, as I said before, the gyro radius of a particle is much, much smaller than the size of the black hole. So we can never do this for realistic scales. But there is another clever thing that you can do. If you remember, the Larmor radius is about 10 to the minus 11 times the typical size of the black hole. So you can actually assume that the particle is a bead on a wire. You can use the guiding center approximation, ignore the gyration or average over it, and assume that the particle just moves along the magnetic field line. That is actually more accurate in a magnetized plasma, because with your typical pusher, you could not resolve those scales, so you better just ignore them. And if you think about a particle radiating, the radiation drives the particle to the 0th Landau level. So the Larmor radius goes effectively to 0. And you see this here in the test that Minggao did. He started with a particle in the magnetic field with this typical Boris pusher. Particle loses energy due to radiation. And here it's indeed just a bead on a wire, and you can safely go to this guiding center approximation. Fabio Bacchini also did this around the black hole and compared it to a very highly resolved Boris method, which you could never do for a production run. And you can see here that the guiding center approximation for the red lines actually behaves equally well to the fully resolved Boris pusher, and that the cyan line, which is a Boris pusher that is not well resolving the gyration, actually gives orbits that are off. So we use this method in a coupled way. Whenever our Larmor radius becomes smaller than the typical MHD cell size, then we switch to guiding center, and else we solve for the full for the full gyration. Right. So now we have the tools. Now let's do some astrophysics. Let's first talk about low luminosity black holes, so the ones that have been observed by the Event Horizon Telescope. As I said before, we have a wealth of information for Sagittarius A star. We also have flares from M87, gamma ray flares, which is very interesting, highest energy flares that we see in the universe, pretty much. And an X-ray flare, so the infrared often comes together with X-rays from the galactic center. So a lot of information that gives us clues about what the plasma could be doing close to that event horizon. The conditions that we can extract simply from back of the envelope modeling of this radiation is that the plasma is collisionless and magnetized, and on top, we know from M87 that there is a large-scale jet, which tells us that if you want to power that jet, you need a magnetic field at the horizon that's roughly 100 Gauss. So those are the observational constraints to keep in mind. Now, how can we get such high energy radiation? Well, there are a couple of mechanisms: gap discharges, turbulence, shocks, and reconnection. Well, this problem has been solved for the sun, or maybe solved is a big word, but for the sun, we understood that reconnection at least plays a big role in these kind of loops that form on the surface of the sun, where magnetic field can reconnect, accelerate particles, and then branch off. So often this mechanism was invoked also for black holes. Reconnection has to happen close to black holes to power those flares. And we have a large magnetic field reservoir that can accelerate and heat particles, so it does make sense. Reconnection is quick, which is actually why it resolved the solar flare problem, the timescales for the solar flare. The inflow speed over the outflow speed, so the rate at which you're transforming energy, is 0.1. So in our case, the outflow speed would be the speed of light, so you're transforming energy with 10% of the speed of light. In the solar context, this has actually been observed with H-alpha emission. We can trace field lines, and here in the magenta and in the yellow, you see two field lines approaching, and a little bit later, you see that they change topology and they formed an X point. So the field lines reconnected and changed their topology, and they created these little bright flashes of light, which we think are plasmoids. I'll get back to that later. So now the big question is, does something similar happen under extreme conditions near the event horizon? So let's first go back to those kinetic equations. We're actually able to solve them for this problem, not globally, but in a local box. So we can just measure, we can just implement anti-parallel magnetic field and see what happens. And this is a simulation by Greg Werner. There are others by people here in the room even. And what you see is that a magnetic field does indeed reconnect, as you can see in this Wikipedia image. The upstream has very high sigma, so there's a lot of potential. The inflow of the plasma goes with the E cross B velocity, and the outflow goes with the speed of light. So you get an accelerating electric field of 0.1 of the magnetic field. So that's a great particle accelerator. You see additionally that the reconnection layer tears up and forms these blobs. Those are called plasmoids, as I mentioned before. And those blobs, they can get filled with those accelerated electrons that then start to radiate. So these blobs can be containers of electrons radiating. Here in a paper by Coronae 2014, you see that the energy that the particles can reach, the Lorentz factor that the particles can reach, depends on that upstream magnetization. So as I told you before, the plasma near a black hole has very, very high sigma. So there is a lot of potential to accelerate particles to high energy. But before they can reach that high energy, at some point they will start radiating. So that you would also have to take into account. Now, can we do that in MHD? This is a project done by my student Alicia Savelli and by Sebastian Salvi, who's in the room here. Can we capture magnetic reconnection realistically in MHD? Well, the answer is yes, I think. And we found out recently that in in particle and cell simulation, so solving this full Boltzmann equation, the current in such X points is carried by the charged particles moving at the speed of light. You can plug this information into your Ohm's law, the equation that I showed you before, and you can get a resistivity that's spatially dependent. And as you can see here, that resistivity peaks in those X points where the magnetic field is reconnecting. If you do this, then you do in MHD also get this 0.1 conversion rate for the reconnection. And in MHD, we have this mesh refinement, so we can zoom the grid really in the regions where this is happening while under resolving the upstream where nothing dynamically is happening. So suddenly it becomes feasible. Well, this is just reproducing what particle and cell does, but suddenly it becomes feasible to use this on large scales for global simulations. Right, and also here you can add radiative cooling, which is something that my student Alicia is working on. Then let's put in those test particles that I talked about before. This is a project that my student Tanisha Ghoshal is doing. And you see here on the right, you see it's a little bit hard to see, but these particles are unenergized here in the upstream. They're green, low Lorentz factor. And then they get into the current, they turn blue, so they're energizing in those X points, and they indeed end up in those plasmoids. So qualitatively, the MHD simulation with test particles tells you the same story as I told you before. And now if you look at the energy distributions, this is the same one from particle and cell. This is the one from MHD. And there are a few things to notice. There is a bump here. Particles accelerate to the upstream magnetization. That's the simple energy argument. MHD can reproduce that. And then the maximum energy is a few times that upstream magnetization. Here is 10 to the 3. Here is 10 to the 3 as well. And the slope of the spectrum here is also similar. So the main properties that you need from your particle distribution to get the radiation seem to be captured by MHD. Right. So now, of course, you want to start doing this around black holes, which comes with its own challenges. So let's start a bit simpler. What do we know about magnetic fields around black holes? Well, I think this starts roughly with Blanford and Znayak in '77. And the main picture here is that a black hole has a plasma or a gas around it. The magnetic field is frozen into that gas. The gas falls onto the black hole due to the gravity and pulls in the magnetic field with it. Now, if the black hole is rotating, the field inside the ergosphere will be pulled around with the rotating frame, with the rotating space-time, and get wound up. So you create an out-of-plane magnetic field. If you're creating a changing magnetic field, you get an electric field, and you can calculate that the electric and the magnetic field are perpendicular to each other. So you create a pointing flux. And that pointing flux points in the polar directions, and that can create the jet that we observe for MED7. This has been simulated with magnetohydrodynamics by many people. This is a picture from Sasha Tchaikovskoy. And you see indeed here in blue an accretion disk pulling in the gas, pulling in the magnetic field with the gas, forming a jet here in the green. Right, so do we see any magnetic reconnection here? I think the answer is no. We don't have enough resolution to resolve those scales yet. But we can think about it. And this is a cartoon by Ashley Bransgrove. If you're accreting, your ram pressure of the gas is larger than a magnetic pressure. So you bring in magnetic flux towards the horizon, and you're piling up magnetic field here in this jet by this rotation effect. So the magnetic field here is getting stronger and stronger. And if it gets stronger, magnetic field ends closer to each other, they will start to exert a pressure, magnetic pressure. So this magnetic field starts pushing and starts shrinking this funnel of accretion here until the point that the funnel gets so thin that you pretty much have a field line here that's ingoing. It's still connected through the horizon here. We cannot see it, of course. And here it goes out again. So here you created a magnetic field line that's anti-parallel to itself, and now is pushed close enough to its own counterpart that this reconnection can happen. And you see this here in a simulation by Ashley. So you see that those plasmoids also form around black holes. Now there is an interesting effect if we again simply look at the Wikipedia image. If you have horizontal field here, think of the base of the jet, that field creates a vertical field here. You see the loops going out and in. And that vertical field, if it can escape the pull of the black hole, it creates a wall. Let's look at the simple reconnection simulation in the box. There is no black hole here. You also see that the horizontal field here is processed by the reconnection layer and it built up vertical field here, right? So that vertical field is exactly what can sustain such a reconnection layer near the horizon. So suddenly we have our solar flare mechanism happening close to the event horizon. Does that happen in reality or in a simulation, which is not reality? The answer is yes. We needed 6 levels of mesh refinement, which you can see here on the left. That gave us an effective resolution of 12,000 by 6,000 cells in 2D, which is very high. And it meant that we could capture reconnection near the horizon by 10 cells over the width of the sheet, which means you reach convergence. So if we zoom in, you see the grid zooming in. Here is the disk. Zoom in further, we see that the disk is pretty and turbulent. Zoom in further, see loads of turbulent eddies. We zoom in further, and now we see reconnection happening on the horizon. If we zoom in further, we see that this reconnection layer here is actually, first of all, well resolved, but second, it looks a lot like a reconnection layer in a box. They're plasmoids, they're merging, and they're doing everything that we expect them to do. Except that this current sheet is not as straight as in a local box. Does it happen in 3D? The answer is again yes. Here you see a standard 3D accretion simulation. It's not standard, it's high resolution, but standard the way it looks. But now see what happens here. This is the magnetic flux on the horizon. So look at this period. Flux is building up. The black hole is accreting. Flux is building up. And here it hits this saturation point where the ram pressure becomes equal to the magnetic pressure, and suddenly the flux goes down. Well, that is reconnection. That is what reconnection is doing for you. It's pushing the flux away from the black hole. So if we zoom in, zoom in even more, then we see again now in 3D, and you can really see it's 3D because it's not axisymmetric. The left and the right-hand side of the black hole are different. So I'm not tricking you. You see that there is a thin reconnection layer with anti-parallel field, and now you see that there are again plasmoids, just now these plasmoids are in the turbulent layer, so they look less ordered. The blue region is the jet. So the main takeaways here are that we have a transient reconnection layer that can push the accretion disk away for a certain period of time in duty cycles. And we have a huge reservoir here of the energy of the jet that can be reconnected and power a high energy flare. I just want to emphasize that this simulation was 5,000 by 2,500 by 2,500 cells, which was, I was at the time, I was at CCA as a postdoc. This was too high a resolution to do at the local cluster here. So we had to do it at Summit, and we used 6,000 GPUs and burned 10 to the 6 GPU hours. So this is not a simulation that you can do like every week. It's a once every so many years. You can try this if you're looking for something specific. It's also only really possible with GPU acceleration. And this was done with Matthew Liska's code. All of that effort, and we still don't know anything about particle acceleration, radiation, or pair production, which is important for this flare. What we do know, or what we can do, is look at the low energy emission. So low energy meaning sub-millimeter, what the Event Horizon Telescope sees. And this was work done by Hajja, a student at Princeton. And this is your typical Event Horizon Telescope image during the accretion phase. Here on the right, you see the radio, the sub-millimeter light curve. Let me play this movie. You see your EHT image. There's some variability, but it does what we expect it to do. And suddenly, you will see the flare happening. So this is where the flare happens. And actually, when the flare or when the reconnection happens, you see that the Event Horizon Telescope image dims. And that's quite interesting because that's not what you expect from a flare. But remember, the flares we're seeing are high energy, X-rays, gamma rays. And the radio emission comes from the accretion disk. But remember, this vertical wall of field is pushing the accretion disk away. So it's pushed out of the field of view of the event horizon telescope pretty much. And you can also see this in the light curve. So those reconnection events are indicated by these gray bands, the gray vertical bands. And you see that the radio emission goes down during a reconnection event. So because you push your accretion disk out and the reconnection is producing very high energy radiation, your submillimeter emission goes down. And this is interesting because there are indications that this is what we see during flares from Sagittarius A star. So it's work done by Maciek Wielgus. And here we observed an X-ray flare with Chandra for Sagittarius A star. And you see that indeed the radio emission observed with ALMA here went down during the flare and went up again after the flare. Well, this is not statistically significant in time. So this is just telling you that it's interesting and that we need more observations like the JWST observations that I mentioned before. But it's definitely interesting that it's not inconsistent with what the simulations are telling us. Right. If we want to model the higher energy emission, the X-rays and the gamma rays, we really need kinetic physics. So we can use a general relativistic particle and cell algorithm where we use the same test particles that I mentioned before, but now we couple them fully to the Maxwell's equations. So we also calculate the contribution to the current and the charge from all those particles and plug that in Maxwell's equations, and we close the cycle. And if we do that, Alisa Galishnikova, who's also here, did the first general relativistic kinetic, the first general relativistic particle and cell simulation of accretion onto a black hole in axisymmetry. And she did a very nice thing. She compared that to a magnetohydrodynamic simulation to see how much the two differ. I'll play the video, so pay attention to the difference between the left and the right. Looks fairly similar. And now the thing starts to reconnect. You see the reconnection layer here, you see the plasmoids, but the reconnection in particle and cell is different. It's a bit faster. So you're pushing out the magnetic flux at a faster rate. So that vertical barrier that you are creating starts to affect the global dynamics of the accretion disk in a different way than in the magnetohydrodynamics. So the small scale kinetic physics, this was ideal MHD. Yeah, this was ideal MHD. The small scale kinetic physics really start to have an effect on the global dynamics of the disk. But now if you think about that resistivity that I showed you before, it could do a local box reconnection with the same reconnection rate as in PIC. So next step would be to reproduce this GRMHD simulation with that resistivity model. It's something that we're doing right now. We haven't done it yet, but I'm confident that at least we can reproduce the global dynamics of these flux eruptions similarly to PIC, but then we can do it in a large 3D setting that PIC does not allow us to do yet. We can learn more from it. If you look at the particles in that simulation, there were electrons, positrons, and ions. And here in this reconnection layer, this is the ion density. You see that there are no ions pretty much. So it's really the electrons and positron pairs that are feeding the reconnection layer. And the ions here in the dark blue are in the disk, in the accretion that is being pushed away. So we can model this paraplasma reconnection, and that's something that Heike Kobian is an expert in. And then we can include all the physics that we need in that Boris pusher that I mentioned before. So we can now do inverse Compton scattering, synchrotron radiation, pair production. We can all plug it in there and see what we get out of it from first principles for reconnection representative for the global MED7, or well, MED7 in this case, plasma. And then Heike managed to produce a spectrum. And now it really becomes quantitative what we're doing, because we see that the synchrotron radiation here gives you a bump that would give you an X-ray flare. And the inverse Compton scattering seed photons here gives you a bump that can give you a gamma ray flare indeed. And still, this is not conclusive. It's not like we solved the whole problem. We need more data. But with the smart combination of MHD and particle and cell simulations, we can get to a point to produce something that you can compare to an actual observation. We can push this a bit further, and this is work done by Anthony Chow and again by Heike. What Anthony did is he did again a black hole simulation, as I showed before, but we are interested now in how many protons would end up in that reconnection layer. I told you before that it's really governed by electron and positron plasma, but we suspected that there would be some protons there. So what Anthony did was he put in a tracer of the accretion disk and of the jet material, where the jet material is representative for the pair plasma, and the accretion disk material is representative for electron ion plasma. So anything that's dark red here represents protons. I'll play the movie again, if it'll let me. So you see the reconnection is happening, you see the plasmoids, and they're still red in there. So there are still protons in there. And then it proceeds, and at some point all the protons are gone, and we're left really with a jet material, with electron positron plasma. So Heike then again did his magic with particle and cell and simulated an electron proton plasma, again under the conditions for MED7. And you see here the particle spectrum for the pairs and for the protons. And now you see that there is a third bump here on top of the synchrotron and the inverse Compton. You see synchrotron emission from ions suddenly giving you a GeV peak. And also that GeV peak can be observed during a flare from MED7. And there are indications from the Event Horizon Telescope multi-wavelength campaign from last year that there is indeed a GeV peak. Whether it's explained by this event, that's to be seen. But the nice thing is that we can at least produce predictions that we can check and compare. All right, so can we model Sagittarius A stars flares? They're a bit more complicated. And this is the same simulation as I showed you before. There is again a reconnection layer forming here, and I plot temperature. But temperature is not the most important. Pay attention to the field lines. They're turbulent here, they're turbulent here. Now I start reconnecting, indicated by the higher temperature, and suddenly I'm creating here this vertical barrier that I was talking about before. So compare the left and the right, turbulent field, and here's very ordered vertical field, right? And now I'm going to show a more complex picture, but just focus on the magenta field lines that are orbiting. So you see them here, and they're moving around in this blue blob. And the red and the blue is density. So we have a black hole in the middle. We have an accretion disk that is red, high density. And we have here a blue, low density blob that is this thing. So this was ejected from the reconnection layer with vertical field here in magenta. The disk field is toroidal, it's green, it's going around. And what you see here is that there are these like fingers, these plumes. And now think of it this way. This is a heavy density disk. We have a low density cavity. And we have gravity pointing towards the black hole. So this is just like your latte macchiato. This is, you see a Rayleigh-Taylor instability forming here. And this blob moves around while these Rayleigh-Taylor fingers are forming on its boundary. So you have a mechanism to act an instability that can energize your plasma. And you have an orbit. So this is, at least this was reminiscent for me of the gravity observations of an orbiting hotspot around Sagittarius A star that's emitting in the infrared. So again, this is not at all yet a smoking gun, but it's an indication that we need to look more closely into the instability that is happening here on the boundary. So that's what we did with Vladimir Zdankin while we were both postdocs here at CCA. we simulated with particle and cell again a slab of low density and high density plasma with pair plasma, electron positron plasma, and we looked at whether this went really Taylor unstable and whether it could accelerate particles. So you see indeed those plumes forming, and those dots are particles, and you see that those particles are being pulled in between the plumes. And you can imagine if you have two really Taylor plumes pushing towards each other, you again create anti-parallel field that can reconnect. So this is again the reconnection layer that occurred here. You see a plasmoid here, but now it's driven by an instability. So Vladimir was able to extract a particle spectrum here, and you see that again the electrons form a non-thermal tail. And if you assume that those particles are emitting synchrotron radiation, we didn't plug it into the simulation here, it's something we still want to do. You can calculate what the synchrotron spectrum would be, and the spectral index that you get from this spectrum roughly matches with what the gravity observed for the infrared emission. So that's again very interesting. This needs to be done in 3D. This needs to be explored way further. I hope gravity will have way more observations. JWST will have observations. We got new time for this spring to again look at infrared flares from Sagittarius. They happen about once a day. So there will be more data. We will be able to constrain this further and to see whether this mechanism makes sense or not. All right. In the last 20 minutes or so, let me focus on some different objects where we can apply the same methodology, but they're a little bit harder than the low luminosity black holes that I talked about until now. So if luminous black holes, there are way more observations. C4 galaxies, X-ray binaries, but they're much harder to understand because radiation plays a dynamic role. So now it's not just about radiation powering a flare, but radiation affecting the accretion itself. Jebba Musoke, a postdoc in Toronto, did a simulation of an accretion disk, again with a lot of magnetic flux, but now she added in the radiation. So similar experiment as I showed before, again, high resolution, but with radiation. And what you see is that due to the radiative cooling, the disk gets thinner. That's expected. We knew that before. We know that for years that that's what happens. But you see a couple of other interesting effects. You see again that the black hole forms a thin reconnection layer. You cannot see it very well there, but you see it here if you zoom in further. Here's your reconnection layer. And again, the black hole pushes out magnetic flux, just like before. But now the flux doesn't stay in this like vertical tube that we had before, but the flux pushes into a Shakura-Sunyaev disk, a thin disk. So if flux is pushed into a thin disk, what does it do? It bends around. So you get, instead of a vertical tube, you get a C-shaped tube like this. And C-shaped field has a curvature, and the curvature of the field gives it extra stability, so it can keep this disk away for a much longer time. So if you now look at the flux on the horizon, same plot as before, now there are no major eruptions that could cause flares, but the disk is being kept out, the reconnection keeps on going, there is a huge reservoir, and we keep on fluctuating like this. But this is very interesting because you have now a reconnection layer near the horizon that could give you a sort of continuous high energy emission. And we observe coronae, X-ray coronae from AGN and X-ray binaries, and we are now investigating whether reconnection in this setting could produce the X-rays that we could link to a corona. It's still inconclusive, but it's very exciting that we're able to simulate these things now. In addition, you see here that there is a strong jet that formed, and not all black holes with X-ray coronae show jets. So this has to be just one of the cases where we form a corona, because there is clearly a strong jet here. But there was a recent observation of a changing look AGN where we saw an X-ray corona forming. Shortly thereafter, we saw a jet forming. It was a picture that I showed in the very beginning of this two bright blobs. So it's very interesting to look more into the radiation that this simulation produces and see if indeed we can link the formation of an X-ray corona with the formation of a jet. But again, for that we really need particle and self-simulation. So we're working on that. Right. Let's look at an even more complicated system. Let's take two supermassive black holes. This is work that's been pioneered by two postdocs in Toronto, Sean Ressler, who's here, he gave a talk about this yesterday at the SPA meeting, and Luciano Combi. And they developed this really neat method by putting together two boosted black holes, developing a metric that is analytic that describes the in-spiral of two black holes. This avoids that you have to solve the Einstein equations, which is yet another expense, and solving the Einstein equations for these kind of systems all the way from in-spiral to merger is still too expensive. And this actually allows you to do it. So you can simulate the accretion disk or two accretion disks, if you wish, of two supermassive black holes in merger, and you can see how they can, for example, form jets. Sean has tested this metric and compared to the exact solutions of the Einstein equations. And you see here, for example, a Bondi-Hoyle-Littleton accretion with a moving black hole and a stationary black hole that are pretty much exactly similar, and also a Bondi, spherical Bondi accretion boosted that doesn't change over time. So this is a very good indication that this method indeed works. And well, there are more tests in a paper pioneered by Luciano. So what can we do with it? One case that Sean did was an extreme mass ratio in spiral. So a supermassive black hole with a black hole in orbit that's 10 times lighter. And we wanted to see if the lighter black hole would give you a quasi-periodic signal by perturbing the disk or the jet. So here's the simulation. Here you see the perturber. It moves through the disk. Here it goes into the jet, and you see that it pushes out material. Here it goes up again. You see it moving here. There it goes. Pushes into the upper jet of the supermassive one, and it again pushes out a little bit of material. So this is something that we're investigating further right now, whether that material that's being pushed out here periodically because of the orbit can give you any electromagnetic signal. The second case that Sean did is to equal mass black holes, and there are two interesting events that could explain, or not explain in this case, predict flares that we want to look for with future electromagnetic missions contemporary with LISA or pulsar timing array information. One is if you have two black holes, you can form two jets, and those two jets at some altitude they can touch each other. And if you think of those jets having helical field, then that helical field will, where they touch, will be anti-parallel again. And you see this here. These are the two black holes. These are the two jets, and you see that the jets here are kind of dancing around each other. And these are cuts through that jet, and you see the two cores of the jet here. And you see indeed here that in between the field is anti-parallel. And here at higher altitude, those jets have kind of merged into one single event. So now you have two jets that are both very highly magnetized that are reconnecting. And also this can happen quasi-periodically depending on how far the black holes are apart and what is their relative spin angle with respect to each other. There's also a non-periodic signal, and this video is more complex, so let me walk you through it. or maybe let me first tell you what you're supposed to look at. The closer those black holes get, the more chance there is that magnetic fields that are in the accretion disk falling onto the black hole could go through both the horizons. So would have one foot point in one black hole and one foot point in the other black hole. But now those black holes are orbiting, so if that happens, those field lines are being wound up. And this is very similar to a magnetar giant flare or a solar flare. Those field lines are being wound up. You create a tube, and that tube can either kink or it can burst open if you wind them up too quickly. So you will see the two black holes, and you will see field lines that are connected between the two black holes. Here in the yellow, you see the field lines connected, and at some point they kink, they disappear. I'll play the video again. So field lines are now connecting the two black holes. They're being kinked here, and now they open up. So you get a very sudden reconnection event that can power a flare that is relatively close to the merger of the two black holes. Also here, the next step would be to add radiation, because we did this for thick disks, while in reality we expect that most of the binaries will also be radiatively cooled and have thinner disks. So that may give a lot of additional effects, as I showed for the single black hole case. Last topic, stellar mass black holes as a result of a merger or a collapse. They can do a similar thing. And while I was at CCA, I did a project with Ashley Bransgrove, putting a dipole on a black hole. And this was a toy problem, because black holes cannot have closed loops on them. That would violate the no-hair theorem. So Ashley wanted to see whether a closed loop, a dipole on a black hole, would still obey the no-hair theorem or violate it. And what you see is, let's see if I can play this again. You don't see the dipole. What you see is that the dipole gets kind of cut open and forms a split monopole. So you have magnetic field going outwards in the northern hemisphere and inwards in the southern hemisphere. And you could think of that those field lines are connected at large distance and are continuously being cut open by the reconnection. So this is a way to get a reconnection layer close to the, or actually at the event horizon. And black hole could acquire this like dipolar field or multipolar field, if you wish, either by a neutron star collapsing, or a black hole swallowing a neutron star with a dipole, or by accreting loopy field, for example. This was with MHD, but actually also managed to do this with particle and cell. And now look at the size of the plasmoids here, typical size. Do the particle and cell, those plasmoids get bigger. That is because your reconnection rate is higher, it's faster. So you're transforming energy faster, so you can build bigger structures. So also here, the balding effect, the expulsion of the flux goes faster in this case. So again, it's important that you have kinetic physics here. But with MHD, we were able to do this in 3D by using, again, mesh refinement really on this reconnection layer only. And in 3D, it looks something like this. So the current sheet becomes sort of a disk around the black hole. There's no accretion disk here. And again, you can see your typical X point and a typical plasmoid here with the helical field forming. So with MHD, we're able to do a reasonable job of capturing the global dynamics of such a reconnection layer on a black hole, but for the details, we need particle and cell. But there are other interesting effects that we can explore with MHD, and that's again a project that Sebastian Selvi did. If you now think of a black hole with a dipole, but the dipole is misaligned. So the dipolar axis is misaligned with the spin axis. It's actually a reasonable thing to assume, because neutron stars are also typically misaligned. That's how we get pulsars. I'll play the video again. So here you see the misalignment, and you start seeing the the pulsation, this is this current sheet I was talking about before. You see a striped windform. You see the pulsation because due to the misalignment, you start seeing, only one part of this current sheet. But you see different than a typical pulsar, if you're familiar with those pictures, the current sheet goes towards the equator. And that is because magnetic field in a star is perfectly conducted. The stellar boundary is perfectly conducting, so the field cannot move on the star. But the black hole horizon is not actually a surface. It's not a perfect conductor, so the field lines are allowed to move, and they actually do. They find the most energetically favorable spot, and they simply move to the equator. So if you have a merger that creates a black hole with a dipole that is misaligned, then shortly after the merger, you will have a pulsating black hole, a black hole pulsar, that dies out, at least in this idealized simulation. Now, you can also do this with numerical relativity. And Elias Most, a close collaborator of mine, didn't believe that this would actually happen. So I challenged him to actually simulate it with this Einstein solver. He has a Einstein solver with the GRMHD code. He did, and I'll show you the first simulation that is not misaligned, where you see the dipole here. This is after the black hole has formed. You see the reconnection layer forms. You see the plasmoids. So also with full numerical relativity, solving Einstein's equations, this process actually happens. There's an additional interesting effect, and that is the space-time here is still ringing. So unlike our case where we put a stationary black hole, here the black hole is still ringing from the collapse or the merger. So it's pulling in a little bit of the field and pushing it out again, which gives you an enhanced reconnection here. It's potentially interesting, right? And here is the misaligned case. So this was a black hole swallowing a neutron star here, misaligned dipole. And here you see exactly this striped wind that's formed, and exactly this current sheet that looks like in Sebastian's case. So also here with numerical relativity, you see that you can form a black hole pulsar that dies out over time, and you see that it dies out about 10 milliseconds after the merger. So it's a potentially interesting electromagnetic counterpart to gravitational waves that can be observed with LIGO. I think we have to be extremely lucky to see them, though. So, but it's worth looking out for. Let's see. Okay, 5 minutes to spare for questions. My conclusions are that the future of multi-messenger and plasma astrophysics is bright. There are exciting new missions coming up. I didn't talk about all of them, but I listed them here. We have X-ray missions, radio missions. Hopefully we can see photon rings of black holes. We have polarization that we're going to observe. We're going to have more neutrino detections, cosmic ray detections, very high energy gamma rays, low frequency gravitational waves. So there's this whole wealth of information coming at us. And to solve the puzzle of black holes, we really require computational plasma physics and astrophysics, as I hope I convinced you of. With GPU accelerated methods, we can resolve scales a bit better than we could before, which is essential if we want to do 3D simulations. And by adding non-ideal physics into MHD, we can actually test some of the kinetic physics with the resistivity test particles and also radiation, which allows you to solve questions that are not doable with particle and cell because of scale separation, or not doable with ideal MHD because the physics is simply not there. To do this, we need to, however, think of numerical methods that are clever, because it's not easy to solve these equations. So we need to develop novel numerical methods to include these essential physics. And that was all. Thank you very much.
Question, or just a reminder when you ask a question to use your seat mic. So,
obvious that resistivity is the best approach for the small scales? I mean, could there be a role for Hall physics or some kind of small scales closure?
Yeah, I would say it as resistivity is the simplest thing you can do. Uniform resistivity is the simplest thing you can do. Developing non-uniform resistivity is one order higher, and if you want to go beyond that, you can include heat conduction, you can include Hall physics if they're ions, particularly Hall physics will be important, and you can go to 2 temperature and 2 fluid prescriptions, and everything will add a layer of complexity, but also a layer of computational difficulty. It would be great to do Hall physics, but the whole thing that we want to avoid was the scale separation. So if you put Hall physics in, you bring back the scale separation. So I would love to have Hall physics, and I think numerically we know how to do it, and analytically we know how to do it, but resolving it, that will be the big question. Yeah.
We have any questions from Zoom?
How would you recommend like sampling over initial conditions to like compare these two observations? Like these were like fixed initial condition simulations. So how would do you think that this could scale to sampling over a variety of initial conditions?
That's a great question. I think I didn't talk about that at all, but I would say the main uncertainty in everything that we're simulating are the initial conditions. We don't know how the magnetic field gets there in the first place. We have indications from larger scale observations from galactic scales, and we have also galactic simulations, for example, a recent one by Phil Hopkins, and actually one by Sean, how stars feed winds onto black holes, or how the accretion on the galactic scale reaches all the way to the horizon, which tells us what initial conditions could be, and they may be very different than what we put in these idealized simulations. And the same goes for merger simulations, obviously, which is even more complicated. So I think what you need to be clever and use the two simulations, the two regimes of simulations of global and well, also global, but more closer to the horizon, let's say, and use that to come up with clever initial, realistic initial conditions. That is also not so easy, because even if you plug in, let's say, a magnetic field that doesn't have a particular structure, then it will not form a jet, for example. So you can think of, and this is a problem that we're trying to solve as well in my group, you can think of how a dynamo could create the magnetic field that would form a jet. This is a question that many people have been thinking about, but you again need extreme resolution to resolve those physics or to resolve those larger scales. So I think you're asking exactly the right question, but I think we're not there yet to answer that question. Yeah.
I have two questions on the like microflares in thin disks, relatively cool thin disks. One question is whether you have an expectation of the resistivity models to change the truncation radius, because your outflow will be moving faster. Maybe there will be more ram pressure from the outflow back to the disk. And the second question is related to the dynamo discussion that you were just having, whether the lack of, let's say, major eruption events is a long-term statement, in the sense of like, once you're accreting possibly larger scale field structure that comes from radii that are, or seeded at radii that are further out, and you give the time for that to accrete, whether this will result in maybe larger flare or like eruption events at that point.
Yeah, both great questions. If you're reconnecting faster, you're blowing out flux faster, and potentially also more. So you could imagine that you would push out the disk further, and you would allow your reconnection layer to grow larger. It's actually something that we're currently even looking at without this faster reconnection rate, whether over time, if you keep reconnecting, you push your truncation radius further and further out. I think that is what happens, but it happens on relatively slow timescale. So testing this with this resistivity model would be interesting because number one, it's more realistic, but number two, it also would happen on shorter timescales, so we can actually simulate it. Regarding the other question, I think large-scale feeding of flux is incredibly interesting, and I would like to study it a bit more parametrically to see what reaches the horizon. Phil Hopkins' simulations seem to indicate, or actually Nick Kaz's simulations where he extended Phil Hopkins' simulations all the way to the horizon, seem to indicate that it doesn't really matter what you feed. There will be a dynamo effect that will create a jet one way or the other. But that's just one case. So it may very well depend on what the field on larger scales looks like, and that may be different for different systems. It may come from stars, it may come from some elliptical galaxy type feeding. We don't know, I would say, but I think it will definitely affect the eruptions. But I would turn the question around. Those eruptions blow out tubes that seem to survive for 100, 500, maybe even 1,000 Schwarzschild radii. And they seem to dissipate through this Rayleigh-Taylor instability, bringing flux back in that reaccretes. So this inner region seems to make its own kind of perpetuum mobile of flux that is being pushed out and reaccretes, which is also something I don't understand. I think the scales need to be connected, but somehow the black hole finds a way to keep reaccreting flux. So great question. I don't have the answer. I would love to find it out with more computations. Robert has a question.
Hey, thanks for the talk. So you mentioned like putting these like prescriptions in MHD from PIC, but I was wondering like, is there also hybrid methods for? Well, I should step back and say like the MHD codes typically have problems with high sigma.
Yeah.
So like, I guess you could put stuff in for the particle acceleration, but like, what do you do about the high sigma?
A great question as well. So what Robert is referring to is that the magnetization is typically very, very large. Think of order of 10 to the 8 or something in a jet. And what MHD can do is about 100. And the reason MHD cannot go beyond 100 is because in your energy equation, you get terms that go at B squared, so magnetic field squared, and rest mass energy, and they get very, very different from each other, such that the rest mass energy cannot be resolved very well anymore. So when MHD creates a plasma that's at sigma of 100, you need to inject some density to keep the code stable, which is a problem for all of us MHD simulators. I didn't get to talk about it, but we developed a method where if that happens, you can switch to the force-free equations. The force-free equations are the infinite sigma, the infinite magnetization limit of magnetohydrodynamics. You ignore all plasma inertia. You just solve Maxwell's equations with an Ohm's law. And we developed a hybrid method that can switch, like if sigma goes above 50 or 60 or whatever you think is a good threshold, you switch to the force-free equations. But then you lose information about your hydrodynamics. So you don't have information about temperature and density anymore. So it solves the numerical problem, but it doesn't solve the information problem. So what we try to do is also solve the hydrodynamics, but we get rid of this energy equation where the problem is, and instead we solve an entropy equation. Entropy equation doesn't feel a magnetic field. So that actually stays stable. I don't think it's a perfect solution, but it seems to work reasonably well for sigmas that are at least an order of magnitude higher than 100. But that's work in progress. But yeah, I think there are ways.
I'm curious about Shin-Ressler simulation. So what finally determines like the jet power? Is it determined by the spin of the black hole or the orbital angular momentum?
It's determined by the spin of the black hole and the flux that you feed to the black hole, both to the power 2.
The merged jet. the power of the merged jet. So imagine that if I have an equal mass anti-parallel black hole, right? So I can imagine that. So at the larger scales, the black hole spin, the equivalent black hole spin is 0. So there wouldn't be a jet. Is it possible?
You mean the combined spin of two black holes?
Well, if I set an equal mass black hole and the spin is anti-parallel to each other,
yeah.
And at large scales, well, the large scale solution would be equivalent to be a single black hole in the middle, right?
Yeah.
And the spin of the black hole should be 0.
I see what you mean. Yeah.
Yeah, and then, well, I would expect the power of the merged jet should be 0.
Well, before merger, you're still talking about a binary, right?
Yeah, the binary.
So before the merger, the black holes will still independently form a jet if they're both independently spinning, even if they're exactly anti-symmetric, let's say. The interesting thing, opposite to what Sean did, is that those jets would have opposite polarity. So instead of two jets with the same polarity, meaning that in between they form anti-parallel field, now those jets, if they were to come close, they would have parallel field, and parallel field would repel. So what I think would happen is it's based on solar simulations of flux tubes that have exactly the property that you're saying. Those two jets would then, instead of merge, they would kind of repel each other and move around each other. So you'd get all sort of additional interesting dynamics, which could or could not give you a signal. But I think it's something that we want to simulate. So yeah, I think it's a great question. Yeah.